Alright, just for synthesis review, we're going to start with a metal. So if I have tin plus oxygen, I know that I'm going to get tin oxide as my example. Now tin is a bivalent metal, so there's actually two options for this. You're going to use charge prediction for metals, same way we did in Chem 1. So if I use tin 4, I'd have SnO2. If I use tin 2, I'd get SNO, and either is acceptable as long as they fit the patterns of the periodic table. It doesn't matter which one you use unless you're given some other information that tells you that. Now, what we didn't deal with in Chem 1 was oxidation numbers for nonmetals. So you had some oxidation number practice in the summer assignment. So for phosphorus, if you look, since it's less electronegative, it's more likely to be the positive. So we are going to use the same idea that we use for metals with the nonmetals. So since phosphorus is in the group 5, again, it'll be 15 on your table. It's going to be +5, oxygen's -2, so again, our guess would be to make that P2O5. So you will see things with nonmetals that don't fit what the predictions are. So don't worry about that too much. As long as you have a reasonable charge, you'd get credit for this type of reaction. And there's not as much emphasis on this, so I don't think you'll see as much of this on the AP exam, but basic ones you might be able to see. For complex synthesis, you're going to have two small compounds that you're going to put together. So you have calcium, oxygen, and carbon. Typically in a ternary compound, which is what you're making when you put three together, metal's always beginning, or the most or least electronegative if it's a nonmetal. Carbon's going to be in the middle, and oxygen's going to be at the end. So again, oxygen typically is your thing. Think of all your polyatomic ions, phosphate, sulfate, carbonate, all of those, chlorites, they all have oxygen at the end. So carbon's going to be the one in the middle, and that's the one that's not going to necessarily follow its rule. So you have to figure out what carbon is based on what this is over here. So since oxygen is -2 and there's two of them, carbon's going to be +4. Now it does match the group that it's in, but it's not necessarily correct. So this is going to be +6. So I'm going to need 3 oxygens because 3 times -2 is -6. A simple decomposition reaction is like aluminum chloride, so it would break down into aluminum plus chlorine in its diatomic state. And again, I haven't balanced these, but I'm assuming balancing is not your biggest issue. You should be able to do that fairly easily, but that's not the emphasis of this screencast, but you really should always balance the equations. What we didn't see in Chem 1 was ternary decomposition. So this is taking something that has 3 elements and breaking it down. So if I had something like barium hydroxide, I wouldn't break that down into barium plus hydrogen plus oxygen plus hydrogen. So I'm going to make 2 compounds with this. Now, if you might be able to guess one compound, so think of this as kind of alphabet soup. So what compounds could I make out of this? So typically I'm going to do the barium, put things with oxygen if you've got the option. Oxygen is very reactive, so and then I'm looking at my oxidation states or charges in the metal and the nonmetal again. And then I'm going to have hydrogen with oxygen again to make water. Okay, again, I have 3 elements here, so I'm going to put iron with oxygen, and I'm going to follow my oxidation rules. So since this is iron +3, and again, I can do that by undoing my crisscross here, so this is going to be +3 -2, so this is Fe2O3. And then I'm going to have sulfur. So just like we had with the acids, I'm looking at what's the oxidation number of sulfur here. So if I know that iron is +3, 2 of them, my total is plus 6. So oxygen is going to be minus 2, and 4 times 3 is 12, 12 times 2 is a minus 24. So you can see how that gets to be really big numbers right off the bat. So I'm going to skip that, and I'm just going to go to the ion, because in some cases it's just easier. So here, if I do it, I'm going to have oxygen at minus 2 for a total of minus 8. And this time it has to equal minus 2 instead of being neutral, because my ion is negative 2. So that means sulfur is in its plus 6. So if it's plus 6 here, it's going to be plus 6 over here. And then I'm going to have oxygen, which it's minus 2, which is going to give me SO3 as my formula for that one. For combustion reactions, anytime you see anything with carbon, it may or may not have hydrogen and oxygen in it, but definitely common to see hydrogen and oxygen compounds with carbon. And oxygen, anytime they tell you something's burning, it's going to be a combustion reaction. So I could have something like C6H12O6 plus O2 is always going to give you carbon dioxide and water. So again, very common processes for respiration or combustion, so very prolific. So just be on the lookout for that. So anytime you have carbon, oxygen, you're going to get CO2 and water. So again, that prolificness of oxygen being the most common thing. We've done a lot with double replacement. Single replacement means you just have an element in a compound. So if I had something like chlorine reacting with potassium iodide, the chlorine is going to kick out the iodine, so you're going to get KCl, and that's your plus 1, minus 1, and then I2. Metals tend to work the same way. I'm going to show you a more complex one just so you've seen one of these. If I'm going to do something that's highly reactive, like an alkali metal with water, it's not going to kick out just oxygen. So if you think of water as being the Mickey Mouse ears, it's going to lop off this hydrogen and you're going to get a hydroxide. So that's the only twist that you may see, and that's only when you have water, is you get this hydroxide.